Greetings, gentle readers, fellow earthlings. Ross Finlayson today with Reading Foundations this June 9, 2026. The previous episode was about the idea of Schroedingerians for the Schrödinger wave functions. It's much like the Lorentzians for the invariant theory and the description of what makes for a metric in a space-time and relativity theories. So the idea that the Schroedingerians and the Lorentzians make for what is, in any so way that it's made a model of the theory of quantum mechanics or relativity theory, makes for so that then there's thus the room in the data and room in the formalism of the theory for as to why then the accounts of making for a fall gravity of the contradistinction from a Newtonian gravity, yet giving the same result in the inverse square is a thing. And similarly, for the quantum mechanics, that it can be a continuous and a deterministic quantum mechanics, simply by fulfilling via mathematical formalism whatever's the Schroedingerian. Then that similarly for the Lorentzian, that being the sum of the space terms, their second partial derivatives, the Laplacian of those, minus the time term, its second partial derivative, the Laplacian of it, with regards to Laplacians and the sum of harmonic functions and these sorts of things. And the metric on the other side, after the sign convention, ds squared or ds dt squared, or variously of the second partial derivative, usually enough the raw differential in these sorts of accounts. That there's a way to make it so and keep it so that the support of the existing theories and their data experiment is left unchanged, but as their suitability runs out, that they hold good in the first order, so beyond that it's lacking or missing. That there's room in the data and the room in the formalism for that for accounts of mechanics that spinning bodies have, that classical mechanics after Galileo's laws, then Newton's laws, are agnostic or ignorant of that. And that in the data, that the accounts of the aerodynamic or the Earth's Foucault's pendulum rotation or the Magnus effect or the Coriolis effect don't together explain the differences to the actual mechanics of spinning bodies vis-a-vis otherwise linear and Galilean mechanics. Makes for so that the classical mechanics is equipped with a greater account of differences of linear and rotational. Momentum is not conserved, that being just kind of the integral of inertia instead of being the derivative of the energy, basically. It has that the formalism has room in the theory for how it can be different, and then the data has room in the science because it's different. And then for things that have otherwise making for the falsification of the theories, there's dark matter and dark energy to do with the cosmological theory, lambda cold dark matter, and relativity theory, or its account of gravity and light put together. Then there's that being solved by having rotational frames being free, for explaining dark matter as being luminous matter, and that it's the centrifugal just falls off outside these larger systems. And then for the dark energy, the idea that everything's receding is the account for light speed, that it's a constant locally in deep space in a vacuum, but that in the greater surrounds, it's basically a function being twice drift velocity of the overall movement. And then as light enters the rotating frames, it goes around several times, the full focus of it of a sort, where light is pure diffraction in a different form of energy than electromagnetic waves, usually enough, a compounded refraction. Again, having it so that there's room in the theory and the mathematics for this, and that there's room in the data to and then bringing those together this way, solving or at least providing a solution for dark matter, and then as a matter of mechanics, and then dark energy as a matter of light's special character. And then for quantum mechanics, there's to be a continuous quantum mechanics and a deterministic quantum mechanics. So the accounts of the Lorentzians and real space contraction and the Schroedingerians and real wave collapse here are figured to be for a realist and a structuralist, someone who doesn't want to be an anomalous fictionalist about being a fragmented pluralist these days with synthetic arguments of the more silly sort that disagree with each other, that lose constancy and definition and these kinds of things. That thusly, that's kind of considered that the term, the Schroedingerians, now has been introduced since the last episode of Reading Foundations, whereas the Lorentzians have been considered about relativity theory here for a couple years or more, because those are what makes models of relativity. And so when studying the formalisms of quantum mechanics, you get to stuff like, well, Dirac says what quantum mechanics is, from the after Born says what quantum mechanics is, with regards to the momentum operators and the definitions of the quantum analogs to the classical quantities. The idea here is then that besides that energy and as being conserved, and the momentum is not being conserved in the kinetic for the classical quantities in the open, or that momentum is conserved in the open in these sorts of accounts. Has that the way then that Born it arrives at, well, we're after our definition of commutation relations, which are anti-commutation relations and non-commutation relations, and then we got the idea of the self-energy and infinite self-energy to deal with, because it would always be there. It always brings itself back into the picture, the Heisenberg and Schrodinger picture here. And then for Feynman is, well, the normalizability of theories. We need to figure out a way to renormalize the theories with regards usually enough to defining the metric and the norm, length and distance, two different quantities, yet both with the same units, and then somehow or the other kind of lost which one is back and forth with regards to the other one. That is so that here there's an account of physics that is one theory, and then furthermore that it doesn't have the usual accounts of falsifications of the premier theories, like for classical mechanics and heft, or for dark matter and then dark energy separately, is about space's character with regards to linear and rotational, and light's character with regards to the linear and rotational, and the moving and the accelerating, this sort of thing. That light is this pure diffraction vis-a-vis electromagnetic waves, is compounded diffraction being different forms of energy, and the optical light is special, truly special. So that then thusly there's one theory, and it's then for mathematics' sake then gets involved also the mathematics of infinity and infinitesimals and these kinds of things. So there's that too for foundations, and there are here in these sorts of accounts multiple models of continuous domains, multiple models of large numbers, multiple models of the spaces of binary sequences, these sorts of things. I asked some people the other day, is like, what is infinity? And one of them said, well, I don't know. It's like, yeah, you do. I said, what is it? And then one person, for example, said it's endless, meaning it's like unendlichkeit, and this kind of idea. It's got no greatest, it's got no last, it's endless, which is a good idea of what infinity is. And the other one says, like, where you can't tell what the zeros and ones are. And I'd never heard that one before. I was like, oh, this is another way to look at it, because otherwise we think of any kind of number as having a binary representation, zeros and ones. And then the idea that, it just doesn't say anymore, fits into some accounts like Simon Stevin's accounts of the p-adic integers. It's like, well, on the little end, it's like when you add one, it's one there, but on the big end, it's after multiplication, adding up to orders of the two operands. So when you're summing things, it's kind of a repeated sum. Is when you're multiplying things or taking powers, it grows on the big end vis-a-vis the little end. So you can kind of tell where the zeros and ones are, respectively, according to the two major operations that give integers, addition and multiplication. Here they're at usually increment and partition, given addition and division as two different organizations and operations. But still, it was a good definition of what infinity is, because otherwise you can, tell what the zeros and ones are. So here with the models of three continuous domains, three laws of large numbers, three spaces of binary sequences or Cantor spaces, three probabilistic limit theorems, and these sorts of counts. Then the other idea of recently was about mechanics in theory and relativity theory. It's like, well, how is it defined length? And how is it defined time specifically? And talking about the system international and the units and their reference values and their definitions. So the idea is this. Besides the NIST, National Institute of Standards and Technology, or Science and Technology, Bureau of Weights and Measures, besides that, NIST's particle data group's CODATA report every couple of years comes forward with fundamental physical constants that aren't just more precise, they're actually smaller, according to the energy and configuration experiment. Like the Avogadro's number actually kind of grows in these kinds of things. Running constants about the measurement of the quantity of time, a most granular quantity, because today in System International or the standard units, it's given as like, well, there's a particular atom that in a particular energy state, according to a particular stimulation, will have a given fixed number of pulses or beats as a clock. And then that defines time as a second is defined as a given number of those. And that's kind of like when the old kilogram was just like, well, the kilogram is a particular reference mass, its weight in the museum in France. And the second was, well, it's according to whatever the clock at Greenwich Observatory says. Okay, so the definition of time is this one way. Today is the SI way since 2019 or something like that. So the second idea is like, well, you can collect time from the quasars, the quasi-stable astronomical objects, quasars, because they variously have a very, very common time base. And then over the course of the sky, they can kind of be used to determine what time is and how to measure time according to how it balances up with those. So there's at least two kinds of ways to measure time. And then a third way is called the synchrotron. And so this is basically a particle collider, and it combines a linear accelerator and a cyclotron to make a means to define what is the interval of elapsed time. So thusly for physics, there's at least three ways to define time. And they all end up agreeing somehow, according to counts of space contraction, which is that length contraction and time dilation always go together, space contraction. And that a relativity theory can have that since it's just a doubly objective relativity theory and it satisfies the Lorentzian. So anything Einstein ever said about relativity theories holds good and these kinds of things. And that's just another one of these things that is like, well, somehow there's three of them instead of one that then goes undefined is because it's considered unique. Really, it's distinct. And then furthermore, it's contradistinct. They're each of these various accounts. So, thusly, the relativity theory and the quantum mechanics can be figured out in a kind of a coherent way to revisit what was left behind. Then, for all these F-Lorentzians, Fizeau and Faraday and Fresnel and Finley-Freundlich and Feynman and Fadio and Fitzgerald, especially with real space contraction. And then these R-Schroedingerians for Reichenbach or relative. or like C. Fitzgeraldians about Casimir or Compton or Coulomb, variously about vacuum pressure, Casimir or Coulomb, as with regards to the another kind of flow and flux, the usual one, and then Compton, and then with regards to like Compton effects and Hall and quantum Hall effects, and these mnemonics then, and then M for like Meissner or Millikan, and these ways to make Lorentzians for relativity theory and Schroedingerians for quantum mechanics, then has an overall account of that's the idea here and how it's to be and how it's to be figured out. Then on to the next book, What's Found. Oh, this is a pretty great book. So in the debate about foundations of mathematics and in the developments and about foundations about mathematics, then there's the constructivist debate and the intuitionist debate. And what that's intended to entail is that over years, these terms constructivist and intuitionist they basically give changes to their meanings over time. Because at some point in time, an axiom system or the ground system, the grounds of a theory's elementary objects will be determined, and then everything after that is constructivism in that. Meaning it's like, well, we're only going to make statements that we can make out of that. And some people will have, for example, that some accounts of strict constructivism have that there's no way to make a proof by contradiction. You can only make a proof by demonstration. And so a proof by contradiction is essentially outside the axiomatic system. That's what it was intended to entail. So things like the quasi-modal logic and material implication, which here are prohibited for direct implication and avoiding the fallacies of material implication and the paradoxes and these kinds of things. Have it that the constructivist view is most people's accounts of putting stuff together and seeing that it fits. Then the intuitionistic view is basically that given an account of the space and anything that's supposed to make a completion in the space, like a limit, an inductive or infinite or continuum limit, has that, well, the space exists, so then the intuition makes her so that something attains to that it meets in the middle somehow, otherwise these inductive courses that would have inductive impasses, not being able to cross the divide in the middle, that thusly the meeting in the middle can happen by these analytical bridges after the intuitionistic results. So Paolo Mancuso's book has it. Mancuso is a researcher in foundations, and I watched a video essay of him some time ago, and I left a copy of it, a link, in the Musitorium. And what it's about is the study of, since, for example, the time of Cavalieri and indivisibles, about non-standard analysis is what it would be called in the 20th century mostly. So in the 20th century, after Cauchy and Weierstrass had made for delta-epsilonics, so they'd given formalisms for what gives real analysis its foundations about otherwise the indivisibles vis-a-vis the iota values or Cavalieri's infinitesimals or Maclaurin's infinitesimals or Newton's or Leibniz's or Price's or Peano's or Dodgson's or the Italian geometers, Vitali and Hausdorff's infinitesimals with real analytical character, vis-a-vis like hyperreals or just not conservative non-extensions of usual accounts of linear real analysis. Its definitions has that there's a study by Mancuso of these various accounts, because one of these accounts is of Brouwer or Brouwer. And so early in the 20th century, as about the time of the formalism of mathematics, is according to a descriptive set theories account, after axiomatic set theories account of something like Hardy's pure numbers, relating and equating that the points of the geometry are like the numbers. On the number line, there are numbers, and there are also points in geometry. And then also after Hilbert saying, well, there's a postulate of continuity, and now there are point sets too. They're points these and their collections of these points, so that each of arithmetic and geometry and algebra have the same kind of common middle ground. So then Brouwer is looking at the continuum again, and he introduces ways to say, well, I'm talking about infinitesimals as they would be, these being smaller than any finite quantity, yet in an infinitude of them comprising a finite magnitude. So like Hilbert's postulate of continuity, which is like, hey, I noticed that since we're making point set topologies for descriptive set theories account, where only everything's a set, and a set would be of points to make what we call a line, that it would have to have an axiom to make it so. And the postulate of continuity of Hilbert. And then the idea that, well, we have accounts of the constructive, what we can make about all these different set theories. We can make things that look like Cauchy's definitions in numbers, the real numbers, equivalence classes of sequences with the property that they're Cauchy. That basically is the same thing as having an infinite expansion, all the zeros and ones of a number. So those are considered the standards. Cauchy defines what real numbers are, and the descriptive set theory gives an account of what those are. And it's so that an equivalence class is a little bit too large to be a set in a set theory, but accounts otherwise aren't quite large enough to have the full definition of the thing without already presupposing all the real numbers existing to define what the real numbers are and that they exist. So Brouwer thusly gets into an account saying, well, if I can't be constructivist, then I guess I'll have to be intuitionistic about it. So when I'm talking about intuitionistic mathematics is that given a connection of connect the dots to fill in the blanks, A to B to C and ... I'm never going to reach Z, but I already know that the alphabet includes Z, or the end. So thusly, I can figure out a way, a symmetrical account, a convolutive account, to make for so that there's a superclassical result that must result to bridge from a constructivistic setting to an intuitionistic setting, and then make it back and forth. Once that's reached, once it's made so that, well, now we have these fundamental formulas about or fundamental theorems about the superclassical that took into account to get there descriptively of going from the constructivistic, kind of like the inductive account, to the intuitionistic, kind of the deductive account, getting those put together and then having the fundamental result, then it starts in a constructivistic course again, because what was an intuitionistic result is now a constructivistic result, or elementary, and then the constructivistic builds on the elementary according to the elements of the resulting new theory. So then Mancosu's book here, I've read it before, and I quoted it quite thoroughly in a number of posts a decade or so ago, and it's pretty good reading. So this is From Brouwer to Hilbert, The Debate on the Foundations of Mathematics in the 1920s, so 100 years ago. But this book was written in like the 80s or 90s by Paolo Mancosu. From Brouwer to Hilbert, New York, Oxford University Press, 1998. Talking about, so the parts are L.E.J. Brouwer, I'm not particularly sure how it's pronounced, but it's always Brouwer. Herman Weyl. Here there was read Herman Weyl's book on levels of infinity and these kinds of things. And it's to be considered the difference between Weyl and Weyl's, three quite different characters for sure. But here that Weyl is the one most interesting for foundations, vis-a-vis accounts of algebraic geometry and number theory, and kind of opinionated accounts of what are settings where there's actually independence results for Erdős's giant monster of independence this year, the great atlas of mathematical independence. So Herman Weyl, talking about predicativity and on the new foundational crisis of mathematics. Brouwer comments on Weyl. And then part 3 is Paul Bernays and David Hilbert. And it's got about Hilbert and Bernays on metamathematics. Part 4 is intuitionistic logic. So that's with Mancosu and Walter P. von Stiegt, S-T-I-G-T. So it mentions like Borel. See, Borel and combinatorics disagree on how many of the sequences of binary sequences are having equal densities of all the subsequences within them. Like you're as likely to find 0, 1 as 1, 0 everywhere. Or you're as likely to find 0 and 1 everywhere. How many of those are like this way? Borel says almost all of them are one way, and combinatorics says almost all of them are none of them are that way. So two different accounts show that there's independence about this object in space. Then you could make an intuition account either way. It's like, well, it's like so, or it's like the opposite way, or you can make an account that it's in the middle, and that's for the square Cantor space and these kinds of accounts. Heiting, H-E-Y-T-I-N-G, on intuitionistic logic, on the formal rules of intuitionistic logic. Kolmogorov on the interpretation of intuitionistic logic. Borel concerning the recent discussion between Mr. R. Wavre and Mr. P. Levy. So after Skolem and Lowenheim, then there's Levy, who's pretty great. He gives a great collapse of these things, saying, hey, if you're going to have Cohen with model forcing that's like it's open and it's independent, it's like, notice you can collapse it both either ways, and now it's a contradiction. Brouwer, intuitionistic splitting of the fundamental notions of mathematics, and so on. Presented here are translations in English of 25 major articles in the debate on the foundations of mathematics that took place in the 1920s. I'm gonna read this a little bit more, and then take into account kind of what gets into it, because it has, for example, it's talking about compactness. So compactness is after completeness. It's like, is there a point at infinity? Like if you have the real numbers and the real number line, I know it's not to scale. I know you can never get there. I know it's endless, but is there a point at infinity that says its value is infinity? Then the natural numbers would be compact if they contained the point at infinity. And there are usual accounts for this, yes, and usual accounts for this, no. But then there's usual definitions of the direct sum of the integers, and if you took the direct sum of infinitely many copies of the integers, there are at least two ways that can be. One is that it's empty, and the other is that it's all of them. And so it's the usual account that you would build inductively and constructively is one way, but then mathematics is like, well, we're going to give a definition. It must be an axiom, and say that it's the other way, because otherwise it would break all these accounts that don't have it. So is there a point in infinity? Yes, in some models of integers is so. Is there a standard model of integers? No, there's not. Except maybe at the very, very end after there's both fragments and extensions. So there's not a standard model of integers without both fragments and extensions, a model of integers. Without all the finite numbers, or with all the finite numbers and with infinite numbers. So compactness, or the fixed point theorem, or other accounts of those being old wrapped as new a bunch of times, or rediscovered and independently, as it may so be said to be discovered, and these kinds of things. That here it's usually given that it's a trivial property of the infinite set of numbers that they contain themselves, and so they are compact. So compactness is defined above. This is Brouwer. He says, does not exist as a property of the intuitionistic continuum or of the reduced continuum. This is clear from the following example. It says, let gamma f be the critical number of the parity-free fleeing property f. So it's ran away, fleeing, and then whether or not it's like a law of large numbers, or it's a law that there doesn't not exist very much larger numbers, which oftentimes they are. Let I sub v equals negative 1/2 to 1/2 for v less than gamma f. Let I sub v equals negative 1/2 to negative 1/4 if v is greater than or equal to lambda f, and lambda f is odd, and I sub v equals plus quarter plus 1/2 of v greater than lambda f, and lambda f is even. So it's just saying that it's making a nesting. Then the interval nesting I1, I2, dot, 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 does not have an element common to all IV. Because just because it excludes negative 1/4 to 1/4 from negative 1/2 to 1/2. And so then that would, and this is after everywhere density and these other ideas of the continuum. Because Brouwer's continuum basically makes clumps, and so it just starts with a point, and it kind of just doubles and doubles and doubles, is his definition of how it begins. And then he says, to reestablish compactness as a property of the intuitionistic continuum and the reduced continuum by means of a logical transformation of definition, we define a predeterminate nesting of intervals, predestinate interval Schroedingerians, as a fundamental sequence of closed intervals, I1, I2, dot, 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 where every I interval, V plus 1 is a subspecies of interval V. We say that a nesting of intervals, I1, I2, dot, 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 is hollow if for every element pi of the first order species in question there exists a definite V sub pi, such that pi cannot belong to I. B pi, we further define free compactness and bound compactness, respectively, as the impossibility of the existence of a hollow nesting of intervals and the impossibility of the existence of a hollow predeterminate nesting of intervals. So the nested intervals account is since the Pythagoreans. It's just an account of after infinite divisibility. There's no smallest because there's always half that. And that's the account of infinite divisibility. And so here, Brouwer's defining this and saying is like, well, I'm just gonna define that there is a predeterminate nesting of intervals as a fundamental sequence, and then he's getting free compactness and bound compactness is independent, and then and here that's because there's already a countable contiguous continuum, the line rules, the iota values, they already have that as a property. So Brouwer's kind of fighting around that, and so otherwise you could just find contradictions in what he said here without having one that already gives his predetermined nesting of intervals. The predestinate interval Schroedingerians. So that's like the equivalency function here, sweet. Then the full intuitionistic continuum is freely compact and the reduced continuum boundedly compact. We can also achieve a suitable logical transformation of definition by describing a nesting of intervals as unlimitedly contracting, unbeschränkt kontrahierend. If for each spread out interval I there is a definite V such that I sub V cannot possibly be a subspecies of I. Further, by defining inversely ordered species S to be freely compacted, boundedly compacted for every unlimitedly contracting nesting of intervals, respectively, for every unlimitedly contracting predeterminate nesting of intervals, I1, I2, there exists an element of S common to all I sub V. In this sense, the full intuitionistic continuum is also freely compact and the reduced continuum boundedly compact. So that'd usually be like limit points or critical points from topology, and basically their existence or not, vis-a-vis having intervals and whether that's contained or not. So that gets into various reasons why there's a point of independence on whether a degenerate interval contains any points or it doesn't. And so a usual idea is that a degenerate interval is saying, well, we're going to take an interval and then have that and have that and have that ad infinitum. Its width is not finite anymore. It's there for any finite value you can show that it's less than that. And then another count is that it's not empty. It's got at least 1 point in it. That's kind of like the account of this this theory here that there exists a surjection from the rational numbers to the irrational numbers. And it's kind of, because otherwise there's an account of the contradiction. So what does this say? It says a function surjects the rational numbers on the irrational numbers. 2006. Abstract. There exists a surjection from the rational numbers onto the irrational numbers. Let Q be the set of rational numbers and P the set of irrational numbers. Q plus the set of positive rational numbers, P plus the set of positive irrational numbers, Q minus the set of negative rational numbers, and P minus the set of negative irrational numbers. So the first statement is there is a distinct Q rational in Q for each P irrational in P. Proof. Let Q sub I plus be the set of positive rationals less than P sub I in P plus. For each P sub H less than P sub H is an element of P plus. Q sub H plus is a subset of Q sub I plus, and Q sub h plus does not equal q sub I plus. Let this quantity be defined as like q not less than I, q sub not less than I, equals q I plus backslash set minus. This quantity, the union of the pH less than pi of the q sub h plus, kind of like Dedekind cuts, but of rationals for irrationals and vice versa. And that also equals this intersection of pH sub pi of this quantity q sub I plus backslash q sub h plus. And then here's the key point about that is making that whether that's empty or non-empty. It is so that q sub less than I is not equal to 0, else there exists a q sub h greater than p sub h in a q sub h plus, or some p sub h equals p sub I. So those would be the cases, and those would not be fulfilled. Thus, there exists q sub I in q sub not less than I. As q sub I is an element of q not less than I, implies q sub I is an element of q I plus, q not less than I is a subset of q sub I plus is a subset of q plus. As q, I'm not exactly sure why that would be necessary to demonstrate, except it just points out that it still holds. As q not less than I plus is not equal to the empty set, and q not less than I is a subset of q plus, for any p sub I in p plus, there exists q sub I in q plus, where q sub I is related to p sub I and not related to p sub j, not equal to p sub I for any p sub j in p. Similarly, for q minus and p minus via symmetry, place less than with greater than, not less than with not greater than, plus with minus, less than with greater than, a positive with a negative. For any p sub I in p minus, there exists q sub I in q minus, where q sub I is related to p sub I, not related to p sub j, not equal to p sub I for any p sub j in p. So there exists an injection phi from p to q proof. As there exists a distinct rational q and q for each distinct irrational p and p, there exists an injection phi p to q. Exists q sub I and q, exists p sub I, p sub j and p. Phi of pi equals qi, pi not equals pj implies phi of pi is not equal to phi of pj. A one-to-one function from p to a subset of q. There exists a surjection rho q to p proof. As there exists an injection phi p to q, there exists a surjection, or I guess that's sigma q to p. And that's the end of it. And so that's just basically as brief an account here as talking about intuitionistic and constructive things about sets of numbers. That this is a counterexample to that there are not. That because the irrationals would be uncountable, then this kind of thing doesn't exist. But this is just a constructivist account that it does exist, vis-a-vis an account that it doesn't, like for compounded compactness and so on, and bounded and unbounded compactness, and these sorts of things. That this helps go to show that when Brouwer has made this sort of account and called it intuitionistic, I can also just say it's so like this, and then either way apply it to the real numbers. So that's kind of written in stone. I typed that up about 20 years ago. Individual signs, variables, signs for communication. This is Hilbert on the new grounding of mathematics. So an account of the foundations, the new grounding of mathematics. And so, yeah, this is some more stuff from these thinkers in the foundation of mathematics, Hilbert and Brouwer and Weyl, and it is via Mancosu that I'll be looking to read this. The foundations of mathematics, says David Hilbert, have long been studied by the most diverse authors and in the most manifold ways. In consequence, splendid sequences of ideas have been developed. Important and enduring results have been achieved. If I now believe a deeper treatment of the problem to be requisite, and if I attempt such a deeper treatment, This is done not so much to fortify individual mathematical theories as because, in my opinion, all previous investigations into the foundations of mathematics fail to show us a way of formulating the questions concerning foundations so that an unambiguous answer must result. Here there's an idea that there's axiomless geometry and then axiomless arithmetic, but they're somewhat deconstructed from the usual accounts of Euclid's geometry and Archimedes' arithmetic to arrive at super Euclidean geometry and super Archimedean arithmetic. So these super Euclideans basically considers like, well, the parallel postulate lets out, or there's a double angle formula at the origin. Because usually the only postulate of geometry that's ever let out is the parallel postulate. And then so these other geometries are just projections in perspective where it's like start out in the points in infinity so that it's just kind of like would curl up and make a circle out of what otherwise is a line. Because the account after Lobachevsky and then for Sierpinski and Riemann about these non-Euclidean geometries has that they're only Euclidean geometries in perspective after projection. So then the other account of this non-Euclidean geometry is saying, well, a straight line is two angles. It's like usually it's like a straight line has no angles. But the idea is like, well, if you're going to equip it with an origin everywhere, now it's kind of got two angles and these kinds of things. So this is the double angle postulate. And it's not normally given as a postulate of geometry, but here it's kind of thought up and discovered that this is another postulate of geometry. And so when that doesn't hold, then you basically get an idea of that it's kind of like an account of, well, what if everything increased? That when you say that the parallel postulate is whether parallel lines never meet in the finite, but parallel lines meet in infinity, it's that, well, there's no angle without intersecting lines, except a straight line has four angles the same. It only has one angle instead of two, and so it basically just makes an account for how there could be projective and perspective accounts of geometry. It's from like all the way at the horizon and peripherally and inside, and which is which there. So axiomless geometry gets a deconstructive account. Then similarly, arithmetic gets a simple deconstructive account because it says, well, it takes increment like the Sumerians to make addition. And then for like the Egyptians have it, then it takes partition to make division. And so the Egyptians have their arithmetic and the Sumerians have their arithmetic. And in the middle, then those meet a couple different ways. Because the infinitely divisible would never arrive at something that's like an incremental thing. It's always having everything. And an incremental increment would never arrive at actually doubling everything because it's always just barely adding one piece there. So that's like the little end and the big end of Simon Stevin's p-adic numbers is just a deconstructive account of numbers. And then, of course, everybody knows, like, well, you just use addition to make multiplication, and then addition's inverse is subtraction, and multiplication's inverse is division. And sure, that's how they meet, in the middle, in the modular. But then it's two operations what meet, not one, is the idea, because that way then it can kind of come from either side of it, you see. So with these sorts of deconstructive accounts of things, then it makes for the intuitionistic settings, which make accessible what these are as the real accounts of the things, why this is so, and it will always be so, and it's always been so. So David Hilbert continues here a little bit. This is what I require. In mathematical matters, there should be, in principle, no doubt. It should not be possible for half-truths or truths of fundamentally different sorts to exist. Well, then he would need like a Comenius language where that's all true already, and then our Coleridge language where we can feebly sort of attempt to describe that. And there's a real truth and all this kind of stuff. Thus, to give us an example of different to give us an example, a difficult and remote item on the agenda, it must be possible to formulate Zermelo's postulate of choice in such a way that the same sense of valid, it becomes just as valid and reliable as the arithmetical proposition that 2 + 2 = 4. So this is kind of the competing realities. So after well-dispersion, and this is kind of like, well, there's a minimality and a maximality. Or here it was as of the compactness. There's like 0, and then there's a fixed point at infinity. And then there's everything in the middle. And so the well-foundedness basically says, like, well, we can start with 0 and increment. And one way to look at the axiom of choice or well-ordering is like, well, there's always a way to bring it back on down, too. And so those actually disagree in the theory, has that this is where you can make accounts of that having both of these regularities, these realities, in otherwise a system where the induction is the only course of account of inference or proof, the truth, they would disagree with each other. And so then having these competing realities makes for super classical results. And these then provide, after an intuitionism in the grounds, they're like, yes, these are Plato's, Zeno's, and Xenocrates' intuitionist accounts of superclassical geometry that lives and is. And then thusly, when going to relate that about what Hilbert said here is like, I got this reality well-ordering that's not the same reality as well-foundedness. It must be agreeable. It is so. As sign. As much so as 2 + 2 = 4. Because you could build all these sorts of ordinary relations in either one of those two. Then the idea that well-dispersion is like, well, also there's a minimality and a maximality, and it's spread out evenly everywhere. You can't really say it's spread out evenly anywhere from the minimal or the maximal in the mesoscale. Like somehow it is. So there's 3 competing regularities and realities, usually called the well-foundedness or foundation, and the irregularity itself, the axiom, or the other one, choice, well-ordering, Zorn's lemma, Ono's, the names for other people who use the notion that there's always a way to relate every element to a set to at least one ordering that's well ordered. Or there's the well-dispersion, Martin's axiom, the illative, the univalent, those also being ways to say it's like, well, besides the pairwise we compare, there's also sort of an infinite union of the things. Besides just the pairwise union, and there's an infinite union. That each of these 3 regularities and realities, as from here, the podcast some months or a year ago about the Rulial foundations, has that in the Logos 2000 bit, that Hilbert would be satisfied this way, but then he'd have to kind of adopt the course of this Thea theory as it is today. One of Hilbert's problems. It becomes just as valid and reliable as the arithmetical proposition that 2 + 2 = 4. I, Hilbert, am of the opinion that the foundations of mathematics are capable of full clarity and knowledge, and that the problem of grounding our science is difficult, nevertheless conclusively solvable. That's a tough one. That the foundations of mathematics are capable of full clarity and knowledge. I think they can be more. They can be replete after the complete, and so that at least there's given that otherwise all these contradictions that can be demonstrated would destroy and see tearing itself apart the theory. That it can be a theory that's consistent and paradox free, then that would suffice, and does. There's still an incredible amount of detail. I mean, it's one thing to say is like, well, how about we just figure it out so that it gives geometry and it gives arithmetic. Go have fun. Everything else is just whatever you say. That's just normal positivist mathematics, according to meeting up with geometry, and then the pure account with numbers and magnitudes being the same, real values and real magnitudes. And then similarly with arithmetic, it's like, could be infinite, point at infinity, and this kind of stuff. As long as it's there, it's given, it's good. So whether Hilbert's clarity and what's the word he put here? And knowledge of the things. So it's like at least it's improved. And then it kind of demonstrably, it makes its own account of uniqueness results that's the thing. The purpose of this interim report is to characterize briefly the sense in which I believe I can attain the solution to explain the means. So he says there's topical interest. Distinguished and highly accomplished mathematicians Weyl and Brouwer are seeking the solution to these problems by following what I believe to be a false path. So talking about the circulus vitiosus, here there's the circulus logicus virtus, the virtuous circle instead of the vicious circle. While talking about real numbers partitions or Einteilungen are used that are determined by whether there exist real numbers with a given property. But in my Hilbert's opinion, matters are as follows. One takes the usual definitions of real number by Dedekind cuts. No, I don't. Sequences of numbers are fundamental series. Yeah, okay. One sees that for the mathematicians, various methodological standpoints exist side by side. The standpoint that Weyl chooses and from which he exhibits his vicious circle is not at all one of these standpoints. Instead, it seems to me he artificially concocted. Weyl justifies his peculiar standpoint by saying that it preserves the principle of constructivity, das constructive Prinzip, but in my opinion, precisely because he ends with a circle, he should have realized that his standpoint, therefore the principle of constructivity as he conceived of it implies it is not usable, that it blocks the path into analysis. So I'd say that probably just applies to Hilbert here as well. In particular, in place of the definition of real number by Dedekind cut, we have the two axioms of continuity, namely the Archimedean axiom and the so-called completeness axiom. To be sure, the Dedekind cuts can then also be used to specify individual real numbers, but they do not provide the definition of the concept of real number. Rather, real number is conceptually just a thing belonging to our system. So Hilbert would agree with me, or he did about 100 years ago already, that real numbers of the complete ordered field here are given as equivalence classes of sequences that are Cauchy. And then as from reading about Finlayson 06 or whatever it was here, a function surjects the rational numbers onto the irrational numbers, then that's an account. It's like, well, I'm just going to be using the same account as of these rational cuts to show degenerates non-empty. So otherwise, you know, they would be in breaking that definition. So the account of intervals and the nesting in the rationals the rationals are huge. They're dense and they're huge in the numbers. And Hilbert here pointedly agrees with what I say about it. And so this would really bring some shade, if not shame, to a lot of people who have that as like, well, once we're given that, then that suffices, and we that is our definition of real numbers. It's like, no, that is not your definition of real numbers. That's just after there is a definition of real numbers saying that the real numbers themselves already suffice to define it according to the density and the topology and the ordering and those kinds of things. So anyways, yeah, it's long known here that like material implication in quasi-modal logic, they're just not included here. This is like so. But it does kind of gratify me to see Hilbert also say so. This grounding of the theory of the continuum is not at all opposed to intuition and Sha'on. The concept of extensive magnitude as we derive it from intuition is independent of the concept of number, Ansal. No, it's not. And is therefore thoroughly in keeping with intuition if we make a fundamental distinction between number and mass number, Maßzahl, or quantity. No, that's going too far. That's having that 1.0 is not equal to 1 is not equal to 1 over 1 and these sorts of things. So the embeddings of the number systems and then the relations to geometries exist, and they're the only reasons we can say that something's like, well, it's 1.0 in this system, and also in this system with these perfect whole numbers, there results that if their result is ratio is 1 over 1, then that equals 1. And also as a real number, if it's exactly and only the number whose times itself is equal to itself, 1, it's not 0, that's equal to 1, 1.000, that 1.000 equals 1 over 1 equals 1, the number, whole number. Because of that, not besides that, is the way I think so. And that's for the integral moduli and these sorts of things. What Weyl and Brouwer do amounts in principle to following the erstwhile path of Kronecker. They seek to ground mathematics by throwing overboard all phenomena that make them uneasy and by establishing a dictatorship of prohibitions, a la Kronecker. But this means to dismember and mutilate our science, and when we follow such reformers, we run the danger of losing a large number of our most valuable treasures. Weyl and Brouwer calumniate the general concept, rational number of function, even of number theoretic function, the Cantorian numbers of the higher number classes, etc. The proposition that among infinitely many integers there is always a smallest, and even the logical tertium non datur. For example, in the assertion either there is only a finite number of prime numbers or there are infinitely many. All of these are examples of forbidden propositions or modes of inference. I believe that, just as Kronecker in his day was unable to get rid of the irrational numbers, Weyl and Brouwer incidentally allow the preservation of a torso, so today Weyl and Brouwer will be unable to push their program through. No, Brouwer is not, as Weyl believes, the revolution, but only a repetition with the old tools of an attempted coup that in his day was undertaken with more dash, but nevertheless failed completely. Now that the power of the state has been armed in strength by a frigate, Dedekind, and Cantor, this coup is doomed to fail. Oh, really? Well, that's casting some shade there. Russell sank Frege. Dedekind was just sunk by Brouwer or Hilbert himself the previous pages ago. And then Cantor is broken open about the independence of the continuum hypothesis. And that being in the account of, for Hilbert, as he was just bemoaning, saying, I got to be able to say that my reality is so, just as good as this other reality is so, in their domains, where they're like to so, how they meet, that it is going to be like so. The atlas of the mathematical independence and the replete realities. Then Hilbert is a little definitely do his own deconstructive account, I guess you'd say. Anyways, this is something to read quite a bit more later and quite a bit more into it. But this collection by Mancosu of the debates in the foundations of mathematics in the 1920s is great because it's the same ones that there would be today if people knew much so what they were talking about. But by now they were just given all this stuff as like, this is the way of things. It's settled. It's already been argued to death. It's done. It's gone through the ringer. It's kaput. It's all figured out again. It's like, well, actually, how you got there is we're finding, for example, that at least these thinkers here are still arguing about it. So then trying to get them all on one page is its own kind of thing. Book in physics, Peter Renton's electroweak interactions, an introduction to the physics of quarks and leptons. Peter Renton. Cambridge University Press, by Peter Renton, Nuclear Physics Laboratory, University of Oxford. Quotes Keats, first published in 1990. Earliest reference to the special unitary 2 symmetry for heavy flavors. Beauty is truth, truth beauty. That is all you know on earth and all you need to know. That's a poet for you. The book has an introduction, strong electromagnetic and weak interactions. So here there was already kind of discussed the difference between the high and low, the near and far, the strong and weak, the distances, the energies, and the strengths of the forces and their fields and these sorts of things. Making counts not when they're of a kind, but when they vary or invert. And so that's just why to make it so for like the accounts of Fritz London and then the running constants, the asymptotics and singularities, why those are like so. And then as like before and as usual, a singularity in a singularity theory is a branch in a multiplicity theory. And as with regards to what's unique in the one, it's just distinct in the other. And that's the way it is in the greater and more superclassical accounts. Toward a quantum field theory, wave equations, propagators, and fields, quantum electrodynamics, scattering electron in a Coulomb field. From Fermi theory to the standard model, so that's like with the Fermi holes to like electron holes, and the idea, as from reading a couple episodes ago about how we got Lienard-Wiechert today, and then what those are intended to be when they start looking at the gaps and the Fermi gaps and these kinds of things. Neutral currents, purely leptonic interactions, deep inelastic scattering, and quantum chromodynamics. After the electrodynamics, the color force, or chromodynamics. Weak hadronic currents, electroweak interference effects, quark and lepton oscillations, the standard model, and beyond. So this has all the definitions that would give what Higgs theory is back in 1990. Testing the standard model, page 522. The calculations in the previous section have been confined to the leading order or Born terms. However, higher order terms are generally significant. These must be considered in precision tests of the theory. As discussed in section 10.3.3, the line shape of the resonance is considerably distorted by QED radiative effects, which gives shifts to on the order of a quantity. The main effect is from the large logarithms associated with the real and virtual radiation from the incident particles. These give rise to terms. In a fully inclusive measurement, there are, however, no similar logs associated with the final state, since the sum is made over all of these. However, this is not the case for a specific channel, where if the delta energy gamma is the maximum energy of an undetected gamma, terms in the natural log of m sub z over delta e sub gamma will arise. Talking about the calculation of correction, so the reduction correction, the reduction cancelism, and these and that. Well, anyways, that's something to get into later. And then perhaps also a bit more to get into this Mancosu's comments and collections of Brouwer, Hilbert, and Weyl, and so on, in the foundations of mathematics. The here today that there was talk in the introduction about the Schroedingerians, about the Lorentzians. So getting quantum mechanics and general relativity theory repaired, because today they've been falsified. If for dark matter and dark energy on the one side, and then you can talk about like the aspect type experiments, and it's like, well, those particles are photons, but they're going faster than photons. And in the quantum mechanics, the theory, just having so that they're still trying to figure out what's going on with that. And then the whole Higgs boson unification is not enough and not done. Then much of the rest of the account is about Hilbert and Weyl, and then for myself, and it's from in a brief account, it's like it's so that the infinite divisibility works both ways, as it were. And that a law of large numbers means not only that there's a number much larger than a finite number, there's another number much, much larger than that as well. That these are the kinds of things. Well then, gentle readers, good day. Goodbye.